Hello, this is section 2.2 and in Calc survey, and we're going to continue our discussion of derivatives. And I know that's a new term, but just to emphasize again, for a function f, we define the derivative function. So notice this new notation, f prime of, we usually write of x, by, and here it is, f prime of x equals instantaneous rate of change. And that's the same as the derivative. And remember the other phrase, slope of the tangent line. So that's when we're talking at a specific point. Okay. Now, sign of the derivative. So if the derivative is positive, then the function must be increasing. If the derivative is negative, so the slopes of the tangent lines are negative, then the function must be decreasing. And if the derivative is 0 on interval, then the function must be constant. Okay. So we're going to see that demonstrated here. So we're going to try to graph the derivative or sketch the graph of the derivative from the graph of the given function. So I'm not a huge fan of this graph because it doesn't show you very well. So kind of imagine if we were to zoom in. But the key thing is the first part until we get to roughly -1, we all agree the function is definitely decreasing. And if you look, if you picked a point, the slope of the tangent line is negative all along that part where it's decreasing. But the key thing, why I wish we could kind of zoom in, is here you don't get a really good representation of those slopes of the tangent lines. As you're getting closer and closer to x equals -1, can you kind of see how they start to flatten out as they approach 0? So the slopes start off really steep, and that's what's happening over here, really high negative numbers. And then as we get closer to x equals -1, those slopes are getting closer to 0. They're flattening out. Then at x equals -1, that's where you have a horizontal tangent line. The slope is 0, and that's where it crosses the x-axis. Now, between -1 and 2, roughly, you can see how the slopes are positive. They start off flat and get steeper. And somewhere here in the middle, is where it's the steepest, and then they start to flatten out again to approach that horizontal tangent line. And that's what's happening here. We don't know how high to go, but they start off flat, get steeper, and this would represent this point where it's the steepest, and then it starts to flatten out again. Right? And then from there, now our function's decreasing again, so we have negative slopes of tangent lines. And again, they're starting off rather flat, so close to 0, and then they're getting steeper and steeper. And you'll notice we have 2 points where the slope is 0, so we knew we were going to have to curve to cross both of those. But the function's decreasing. Notice your slopes, your derivative is negative. Where the function's increasing, your derivative is positive, and then decreasing, negative. Okay? So let's try another one. So in this case, this function is a straight line, always decreasing. And we can actually find the slope. You go down 2 to the right 2, so the slope's actually -1. So you're just going to simply draw a horizontal line at -1. Pretty nice, because anywhere along that line, the slope of the tangent line is the slope of the line. Now in this case, from the left, you have a slope of -2. So you'll notice I've done a horizontal line at -2 until we get to x equals 1. And then to the right, you have a slope of +2, so it jumps. Now we have an issue at this point. And I'm going to raise 2 arguments. First, you could draw infinitely many tangent lines or lines through that point. So which one is it? And another argument that I like better, if you're standing at that point, how can you be decreasing and increasing at the same time? Or which is it? You can't be standing and increasing and decreasing, speeding up or slowing down at the same time. So when this happens, when the slopes are different from the left and the right, or we call it a sharp turn, the derivative does not exist. So you'll notice on the derivative graph, we've put open circles here to indicate the derivative does not exist there. All right. So let's look. Okay, here comes another table problem. Infamous table problems. Okay, given the numerical values shown, find appropriate values for the derivative of f of x at each of the x values. Now remember, table problems, you have to use the data in the table. Can't make up any data, can't assume what happens between what you're given. Use the data in the table. So, and remember, if you just have these points, you have to rely on slope. You're going to use slope. So at the endpoints, you can only use the point next to it. So you find the slope here. That's how we're getting this value. And then if I jump to this endpoint, you use the point to the left. That's where the 3/2 is coming from. Now the nice thing is all the x's are going up by 2's. So I can use that shortcut where to get the slope at 2, I'm going to use the data it's between. Okay, so that's where this is coming from. And then to get the slope at 4, I'm going to use this data. To get the slope at 6, I'll use the data on either side, right? And you can only get away with that trick when it's increasing by equal increments. All right, so you'll notice the derivative is negative, 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 and then it switches to positive. So look at your function. Decreasing, but then it increased. So now your derivative is positive. It's increasing. Isn't that cool? So where is the rate of change of f of x positive? So in this case, where was your derivative positive? We'll say 6 to 8. So here's where you don't want to say 5 to 8. You don't know if that's where it switched. So just stick with the data that you know. All right, where is the rate of change negative? Again, from 0 to 4. If you put open parentheses here, that would be fine too. Okay, and then where does the rate of change seem to be the greatest? Now be careful, don't let the negative and positive numbers fool you. You want to go with where is it the highest number? And in this case, it's at 6. Okay. Where is it the greatest? I guess you could look at the sign too, but you have to be careful with the wording. Alrighty, so 3 methods, interval to the right, interval to the left, and that's what we had to do at the endpoints. And then when you're within the inside of the table, use both and average together. Use the best, what's called the best estimate. Okay. All right, so let me face up here. So guess a formula for the derivative. All right, so we're going to see if we can figure out this. So notice I just picked a random x value. We're going to find the slopes. So the slope of the tangent line, or the derivative at 1. So, and I did 1.001 away. So remember, we're technically finding the slope of the secant line. And then from there, we're saying that was close enough that we can say it's a really good estimate of the slope of the tangent line. So we went through and we used our function to get the y values, x values. So you get 3.003001. So that's the secant line that we're going to say is pretty close to the slope of the tangent line. I think we can all agree it's 3. Did the same thing at 2, got 12.006. And then I did the same thing at 3, got 27.009. All right, so looking at the integers here, 3, 12, 27, what's going on? Well, they all have multiples of 3, so I could write 3 as 3 times 1. I can write 12 as 3 times 4. I can write 27 as 3 times. What's going on here? You have 1, 4, 9. Those are perfect squares. So it's looking like the derivative is probably 3x squared. Now, we're only going to do that. I think you have one problem in your homework where it challenges you to do that. But we'll find this derivative really quickly. And if you've taken physics, you knew immediately what the derivative was. So, but this is really cool to see how you can use the pattern to help you try to figure it out. So just think of it as a little puzzle. Okay, well, if you have any questions, please email me.